start from the carbon structure that is all saturated with all single bond. Now a molecule have two parts, kind of break off from this all saturated structure. The end product is alkene. Okay, so we're losing the two pieces from this molecule and get into a planar two-dimensional structure. So it's very important if you have a model or you get used to rotate the molecule in your head. This is the essential skill to understand the reaction stereochemistry. Okay, how does molecule react? And so the elimination reaction, in this lecture, I mainly go over how does elimination takes place, what are reagents, what the substrate, the steric effect affect the elimination, and then finally we have compared the elimination and substitution, because some reagent can have both reacts, can react both ways with the same substrate. And so toward the end, it might get into complicated. We start comparing the contrasting. So the Leah Forsai, she has multiple videos on this, and you can check that and make sure to keep up Zeppelin homework on this chapter. So elimination reaction is the molecule lose the hydrogen with the X being the leaving group. And these two, the hydrogen and leaving group, are next to each other. And so when this elimination takes place, both hydrogen and leaving group, keep in mind, leaving group, best leaving group come from the strong acid. So now the leaving group combined with the proton together become the acid, and left depart. The remaining is they give us a unsaturated alkane as a product. The elimination reaction is the opposite to the addition. The addition reaction later we'll get into, actually very soon in the alkene chapter we'll see the addition reaction. The elimination reaction, it is the entropy increasing process. You can see that from one molecule become at least two molecules. Here we see the one reactant become three species, one alkene and two ions compound. So this is the entropy increasing process, and that's why the high temperature is preferred. High temperature really promote elimination. And also the removing proton by the base really can promote the elimination reaction based on just the Chatillon's principle. Base will remove the proton. So for the elimination, it is we have two ingredients. One is the base, because base to remove the proton, and also the substrate is a nucleophile with the with a leaving group. Okay, this is basically the substrate with a leaving group. You need two of these. The base eventually take the proton away. It sounds like a simple proton transfer reaction. And so the reaction, this is example, use the cyclohexyl bromide. Reaction with base. The hydroxide is a good nucleophile and also very strong base. So it actually can have two reactions with the same halides. Can be just a substitution. The hydroxide nucleophile attack the carbon, remove the bromide, and build the OH bond. That will give the alcohol. The other way reaction is the alpha position with the bromide, the beta position. The carbon next to the carbon with the bromide, it loses hydrogen and form double bond between these two. So that is the elimination. They call this beta elimination or 1,2 elimination because the two carbon atoms next to each other have the reaction, lose the HBr reaction. HBr is the product. You can regard it both. And for the elimination, very similar to the substitution, it also have the E1 and E2 process. The first one is the a concerted one-step process. The base attack and leaving group break at the same time. And so this reaction, if you use arrow pushing, it is base use lone pair form bond with the hydrogen. And the hydrogen bond, this bond break to help form the double bond. And anyway, to maintain the octet, this bond need to break. Eventually form the alkene and the leaving group. So that's the one-step proton transfer. Proton transfer bond breaks form the double bond. At the same time, you have the leaving group lost. This reaction can also form in a two-step reaction mechanism. That is when you have a good leaving group. We have good leaving group and form a stable carbocation, just like in the SN substitution reaction, SN1. Tertiary carbon here with a 3 carbon bound to the same carbon. Tertiary carbon can lose a proton and form the carbocation. And with the carbocation, then you have a base. The base, okay, the first step is just to have a leaving group. Second step, the base come here, pick up the hydrogen. And since the hydrogen gain electrons, hydrogen will give away the electron to form the double bond. So that's a two-step mechanism involving the carbocation. It's very similar to the SN1 reaction. So these are stepwise mechanisms. So the E1 reaction is the first order kinetics, similar to the SN1. First order kinetics and the reaction concentration only depends on the substrate, the one that was a leaving group. With a leaving group. And so this reaction is just depends on the substrate with the leaving group, nothing to do with base. And that's the E1 reaction, the same way as the SN1, in a very similar way. The reaction mechanisms, the first step, dissociate, lose the leaving group from the carbocation. And the second step, the base take away the protons. It's fast. So it's very similar to the SN1. The E2 reaction, it is a second order reaction, concerted. The base take protons and form double bond, leaving group leave all 3 arrows in one step. Okay. And the final product, you have the alkene and leaving group as one step. This has only one step in the slow step, which is also slow step. That's why the reaction rate is proportional to both the substrate with leaving group and the base, just like the SN2, very similar to SN2. The only difference is the product is different, and the arrow is different as well. The arrow is different. So at this point, now if you make a table, compare all these, you'll find something interesting. They have some similarities, but there's a difference. So when you memorize multiple information, huge volume information, you should make a table. As here we'll make a table, compare the E1, E2, SN1, SN2 reactions. Okay, so the reactions. Before I move on, it's kind of a review on the primary, secondary, tertiary. It depends on the carbon that link with the functional group, number of carbons linked with this alpha. The carbon with linked with the functional group of interest is we call it alpha carbon. And depends on how many beta carbons on this alpha, we have a primary, secondary, tertiary, just like we did this before. But in the elimination reaction, what we find out it is the with the tertiary substrate, the reactions is fastest, is most very fast reaction. This reaction is we're losing the hydrogen on the beta carbon. Okay, we're losing the hydrogen on the beta carbon, such as this. These two dissociate, and so that's basically what we find out. That beta, we have more beta hydrogen, beta carbon. The reaction is faster. And so for the E2 reaction, the single step base attack, leaving group, form alkene, all happens in one step. For this kind of reaction, the tertiary substrate is preferred. And so the tertiary alkene, easiest to have the elimination reaction. And what do we find out? It is this reaction proceed a transition state have a lower energy when you have tertiary carbon. And transition state have lower energy, that's low activation energy barrier, that's kinetic favorite. Okay, if you remember this. But in this chapter, we actually do not really ask you to memorize which reactions kinetic or thermodynamic favored. But for the tertiary carbon lose the beta hydrogen, it is both have a lower activation energy and a lower free energy of the product. It's also thermodynamic favored. That's what we find out with this reaction. And so this is basically a comparison about the three different substrates, first, second, and third. How each one, the transition state, compare with others. So this is a primary. First one's primary. Okay, my zoom control bar is kind of getting away. I need to move that way from here. Still getting away. I need to move the whole thing out my way. Can you see there's a kind of a rectangle blocks kind of in front of the screen? Sometimes happens. Okay, so this is the primary, secondary, and tertiary. Both the product and the activation energy are lower than in the tertiary than the primary, and therefore it's faster. So this basically explains why this kind of tertiary carbons react as fastest. And the reaction have the transition state. We should know the transition state. For elimination reaction, the transition state is base attack hydrogen, the proton transfer transition state, and at the same time, this bond will break. Okay, this bond will form. This is a forming bond. This bond is going to break, and this double bond is also forming. Finally, the leaving group, it will break later. So there are 4 arrows. The 4 bonds are going to involve in the transition state. 4 bonds in the transition state involved. 2 of the bonds is forming, and the 2 bonds are breaking. So that's the tertiary is the most fastest. That's compared to relative reaction rate. Selectivity, this is getting interesting. And today, I think it will stop here, the regioselectivity. So regioselectivity in organic chemistry, again, organic chemical reaction, typically slower. And since it's slow, it easily gets distracted. There are several competing pathways. And so when you have several competing pathways, one pathway is more preferred than the other, give you the major product. And if one pathway is more than the others, happens in the several different locations, the preference of such location, we call it regioselectivity. Regio means the region. Which region is more preferred for the elimination to take place? And so the elimination reaction, this is the example. This example there is tertiary carbon, and you have alpha carbon has three carbons. And so for the elimination reaction taking place, it actually have two different products. Okay. The first of all, if this hydrogen is removed, lost, and form double bond, then we're going to lose this bromide and this hydrogen. Lose these two, it'll form this bond, which is we call it Zeitsev product. Zeitsev is a Russian chemist, and he first discovered the pattern when the elimination reaction takes place. It seems like always have a pattern, and that pattern is he called it Zeitsev product. There's a name for that. Zeitsev product, it is the end of the alkene. The alkene double bond has more alkyl groups. Substituted means the more alkyl as substituent. And so most reactions follow this pattern. It seems that they always do that, always form this double bond by losing this hydrogen. Okay, the other reaction is we call the Hoffmann. The Hoffmann reaction is, you notice there are two methyl groups. The methyl group, each one has only linked with only one carbon with this. But we have a such hydrogen. So if the acid take away the proton from these two, one of these two methyl groups, you will get the double bond. Okay, the arrow pushings go take away the protons, then the bond forms. The base attack take away, and then this leaves. If you go this way, you form double bond between the methyl group, methyl carbon, and the alpha carbon. So you get this product. Okay, sorry. This is actually, if I break this bond, build this bond, maybe better, more correlate to this. But anyway, it's the same molecule. This product is normally a minor product. But the Hoffmann is a chemist. He noticed under some reagents, if you pick some reagents, the base, very special base, you can make this product as a major product. And this product we call a Hoffmann product. The difference is if you take a look at the alkene, there's only two alkyl substituent. Compare with Zeitsev. Zeitsev, you look at the alkene, have three alkyl groups attached. So that's the difference between the Zeitsev and Hoffmann. And we should know these two reagents, these two products, and what give you these two products. Okay, this is something interesting. We haven't had this kind of experience before, but here we see in the organic chemical reaction, by using different reagents or different solutions, different catalysts, different temperature, different solvent, we can get a completely different product. And here we go. This is the same tertiary bromide, alkyl bromide. With the base, we will get two products, possibly two products, both elimination reactions. And the first one with more substituent is we call Zeitsev reaction. The second is Hoffmann. And so the results is very interesting. if you use a base that is S-oxide, which is a conjugate base of ethanol. So it's a very strong base because ethanol is a very weak acid. When you have this base, we'll get a main product as Zeitsev product. This is the main product. And Hoffmann is a minor product, much less than half. Okay, and then we use something different. This is a conjugate base come from terbutanol. This comes from the alcohol as tert-butyl alcohol or terbutanol. Give you this base. And most commonly we use potassium as a counterion. So in the organic chemistry, we just use a short T-book. A terbutyl oxide, butyl oxide, and with potassium as a cation, counterion. So it's basically, we should call that potassium terbutanoate. Anyway, it's basically one of the organic chemistry we name that. But normally we just call that T-book. This one, over time, we need to remember. This is what we need to know. Because T-book give you very interesting results compared with a normal base. Because T-book, this base, give you the major product as a Hoffmann elimination. Okay. For people to study organic chemistry, it can be either overwhelmed or you liked it. But here's the part I liked it, because the results depends on what reagents. And like we discussed before, it depends on solvent, the agents. But this is actually with two different agents. You get still two same product, two elimination product. By using two different reagents, you get different ratios. With the terbutyl, such a big bulky base, you get a Hoffmann as a major product. And you can see the results even more dramatic if you use the, this is also a, this carbon is very similar to T-box, except you have instead of methyl group, you get ethyl group. So basically 3 ethyl group attached to the same carbon. This base is even more bigger. Okay, so if you draw the structure, that's how it looks like. You have bigger, even more chunks because ethyl groups. So when you have such a big alkyl group, Hoffmann products, even more obviously, is predominantly Hoffmann product. The ratio is even more interesting. So this is a regioselectivity based on the base. What kind of base did you use? Okay, we need to remember this. Whenever you see the T-box, you use the preferred as a Hoffmann elimination, where you get the alkene has a fewer substituent. So what caused the difference? Okay, this is the again, the difference is caused by the steric effect of the base. Okay, when the base is not sterically hindered, a very small base basically means a very small base. Small base, such as the mesoxide or S-oxide, mesoxide, and S-oxide, ETO minus S-oxide. These are very common strong base in the organic chemistry because they come from the cheap alcohol. You just use some sodium metal to react with them to make those base. Those bases are very small because the methyl and ethyl groups are small alkyl groups compared with many other groups. And so when you have this group, the small alkyl groups, it tend to attack the carbon with, tend to form carbon with more carbons is attached. Okay. That'll give you the main product. The reason because you go back to several slides, you can see the elimination reaction, the more carbon attached, more higher degrees of carbon on the central carbon, then it's more preferred in the elimination. So the reaction should happens on the carbon with more carbon attached. So that's kind of going to because we're taking away the proton from this carbon, take away this hydrogen by the base, and because the multiple substituted alkene is more stable, you get a Zeitsev, you get this product is major product. And so even though, by the way, even though the methyl group here, each one has 3 hydrogens, and here you got only 2 hydrogen, still number doesn't matter. The double bond is still preferred happens between these two. Even though the chance of a attack, take away the proton from those two should be much higher, 3 times as higher, but still the main product are the Zeitsev product. So because when the base attack on this hydrogen, there's a methyl group here, they're getting away. There's a big methyl group, make it difficult for the isoxide, whatever base. But isoxide, small base are small enough, it's easy to approach from this direction and react. Okay, when you have very big base, then the story will be completely different. The big base, there's no diagram show it, but let me show in a different whiteboard. When you have big base, what happened? Bromide, and here's the methyl group, CH3, CH3, CH3. Hydrogens here. There are 2 hydrogens. You're gonna lose 1 hydrogen. So when the base attack, the base will take away the hydrogen from this end, from this direction. When you have very big base, big bulky CH3, they turn butyl. Those base take space. They're not just one dot, they actually take space. This is how, if you consider the hydrogen, how the shaped molecule looks like. And when they attack, there's a hydrogen here. So when they are attacking to take away hydrogens, for this base to approach this hydrogen, keep in mind these are the methyl groups. They take space. They take space. So these 2 methyl groups make it difficult for this base to approach. Okay. There's a repulsion between these 2. If you attack to this hydrogen, there's not so much interference from nearby LQ groups. So instead of going this way, the attack happens to a more accessible methyl carbon. Take away proton from the methyl carbon instead of from this carbon. So that's basically why the Hoffmann. You explain why the Hoffmann give you the produce the other product. And so what else base we have? The T-book. T-book is one of the butyl alcohol gives the base. And the other ones are it's actually a weaker base because it is a amine. the basicity is similar to ammonia. So these are actually weak base. But even though they are weak base, it may take a longer time to react. But because these are very bulky, takes a lot of space. Methyl group here, methyl group here, methyl and methyl. Make that ideal to take away proton from only the less substituted carbon. And same with this triethyl and trilethylamine. The common discussion in our class, in the assignment, are the T-book. When you see T-book in those reactions, the reaction takes place through the Hoffmann, give the Hoffmann product. And so that's the basic selectivity. We can go a little more. If the reaction give you the alkene, and because considering those, this is actually alkyl halides, all saturated bond. So those bonds can freely rotate. If bond can freely rotate, then when you finally lose proton, lose hydrogen, lose the leaving group, give you the alkene, you might have two products. It's either cis or trans. Either cis and trans. What to find out is the trans is the main product. The trans is the main product. The reason because in the cis, there's a steric repulsion between these two. Because these two are close. So when you have a two alkyl group on the cis configuration, they are, if you look at the Newman projection, it is given the fully eclipse. That's the, if hydrogen there, hydrogen, and these to the CH3, and the other also CH3, you got a complete eclipsed structure. The energy is high. So therefore, the cis product is higher energy. And because cis product higher energy, the transition state for the cis also have higher energy. Actually, the main reason it is because in the transition state, even being the alkane, you got a fully eclipsed structure between the hydrogen and the give stronger repulsion. And just like the alkane we discussed, the fully eclipsed, you get a higher energy. So therefore, the transition state also have high energy. And that makes them both slower and slower reaction for the cis. And also the final products is higher energy, less stable. So these two basically, trans, it is both thermodynamic and kinetic favored. Both kinetic and thermodynamic favored. And when there are two beta hydrogen can be removed by the base, the trans product is a major product. It's just because trans, there's a less alkyl group eclipse. Basically, there's no eclipse for the trans configuration. You got a two bulky, the very bulky alkyl group as across the against each other, 180 degrees from the double bond. So there's no eclipse like the one we see the Newman projection when the methyl group, alkyl group exactly overlap with the alkyl group across the other carbon. That's eclipsed. Eclipse is more high energy, unstable. Same with here. They tend to have a trans. And so that's last time we stopped here. And the last time we go over the Zeitsev Hoffmann elimination. So you can see the if there's a multiple different carbons, each have a beta hydrogen, then depends on what size of base. Very bulky base, they tend to give the Hoffmann elimination to take away hydrogen from the less carbon attached, less steric effect. If with a small base, they give a Zeitsev elimination. So that's what we covered last time. It's already pretty intense. Okay, so that takes some time to, you can see the organic chemical reaction typically is very high activation energy, which means the reaction slower. So that means when the reaction is slower and there are multiple pathways, each can have a significant reaction product. And so we continue on the stereoselectivity for trans. Okay, so this is a little practice on, let me see. Yeah, I have the answer key for this. It's basically depends on what size of base or what kind of elimination can take in place. The one to the left, these are the Hoffmann elimination product. The hydrogen and leaving group, the leaving group is a bromide. Hydrogen, we have multiple locations. There's a 3 hydrogen here. There's 2 hydrogen, which is same as this. See, these two exactly same equivalent. So it's basically elimination taking place when lose hydrogen either here or here. Because losing hydrogen here is the same as losing hydrogen here. And so by losing those hydrogen, we can have double bond here or double bond here. Because this is bulky. Bulky, that means take away the hydrogen from the least substituted beta carbon. So it's kind of fun to watch. After losing the bromide, you have pseudo-methyl group here. And with a bulky base, we take away the hydrogen from this carbon. And this carbon name was a methylene cyclohexane. This is kind of it's a CH2 group, so it's a methylene group. Methylene group is basically methyl and alkene together. It's the one carbon with double bond found with other structures. With a small base, this is the methanol, lose the proton, gives a strong base, methanoate, methoxide, sodium methoxide base. This is small base, so take away hydrogen from the more substituted from here. So give you this as a major product. Isn't it fascinating? Organic chemistry, you have a reagent, you have to think, and what the reaction pattern is, and then predict. Different conditions give you a completely different product. So unlike what we learned in the general chemistry, it's mathematical. Basic theories is just simply apply. You got only one reaction product, but with organic chemistry, it becomes much more interesting. Okay, so with this is leaving group, and how many beta hydrogen we have? We have beta hydrogen here, and we have beta hydrogen here. So depends on what kind of base. This is the very bulky base, so take away the hydrogen from the least substituted carbon from this one. And then this is a leaving group. The leaving group just left. And so with the Hoffmann base, we get the lose hydrogen from this carbon. Because this carbon have 2 other hydrogen, no more carbon substituted. Less steric effect. With a small base, it'll take away the proton from the more substituted, because thermodynamically more stable when the alkene double bond has more methyl groups around. So the small base take away this hydrogen. And also give you the trans product. Okay, keep in mind the trans is also, regardless, is more preferred than cis. Because the eclipse, the steric effect. The trans cis, if you draw the Newman configuration, the cis, it looks like this. Okay, remember the carbon is the trigonoplanar. You don't have the other group. Whereas trans is RH HR. These two bulky alkyl groups stay away from each other, less steric repulsion, so they're more stable. Trans is more stable, like we've seen before. So that's E2 product that goes with the Hoffmann, Zeitsev, and cis and trans, the preference for trans in the final product. Okay, so those are when there are multiple beta hydrogens available, which beta hydrogens being removed. Now we're getting the interesting. This is the situation. It's relatively simple, but we have to be able to rotate the molecule, rotate a single bond in our head and put on paper to predict what is the product. When the substrate have only one beta hydrogen, okay, only one beta hydrogen, that means you have only one product. There's no regioselectivity. What location, you don't need to decide what location to form double bond like we see in the last slide. But here, when we give you the structure, like such as this, a three-dimensional bond line structure, like this. And there's only one beta hydrogen can be removed. The beta hydrogen you were given may not be the perfect location for the reaction to take place. So we have to be able to rotate the bond and then line up the beta hydrogen so that it be perfectly be removed. So this is the we have a leaving group here, and this is the alpha hydrogen. Alpha hydrogen will not be removed, only beta, and there's only one beta because this is beta carbon, and this is only one beta hydrogen. There's no other beta hydrogen. This is a methyl group, it's not hydrogen. And this beta group, beta carbon, have a 3-methyl group. It's basically a tert-butyl group. So therefore, you can only lose a single beta hydrogen to form the alkene. And by losing these beta hydrogen, we could have a E or Z alkene product. E and Z is in the alkene chapter. The E and Z is equivalent to the cis and trans. Okay, we did not really officially introduce E and Z yet. The E is equivalent to trans, and Z, of course, equivalent to cis. And so with this bromine is leaving group and this hydrogen leave the same time, we form double bond here. So this bond will break, form double bond. And we can just write down we'll just leave about leave the E and Z later. Let's write down what would be the alkene can form after both leaving group beta hydrogens left, without thinking about, okay. So the first, this is a very good exercise. It can be challenging, okay. We're gonna remove this hydrogen. And remember, once you form the double bond, this carbon is trigonoplanar, okay. It's trigonoplanar. See, this methyl group, it was dash. After remove the hydrogen, now it becomes in the down position, in this position. Okay, the organic chemistry is 3-dimensional structure. Sometimes you have to wrap your mind to figure out what is it we're getting. Okay, and so this is the left-hand side. This carbon. The right-hand side is the bromine, hydrogen, the tert-butyl group. Okay, we're losing bromine and keep the hydrogen. So after losing bromine, let's just write down, regardless of how they change. This will be the first product. After losing the bromine and beta hydrogen. So what about isomers? E and Z products are basically isomers. By rotating, actually this double bond cannot be rotated, but we assume, we can't pretend double bond can be rotated. And then we get an isomer. That's another stereochemistry isomer, the stereoisomer. We keep the same, the left-hand carbon have the same up and down substituent, but switch the right hand. All right, so that's basically the two products we'll get by losing the bromine and beta hydrogen. And so which one's cis, which one's trans? The trans is equivalent to the E is equivalent to trans. And trans means the hydrogen stay on the opposite side of the double bond. And the EZ designation is more about based on the hierarchy of the groups. And the hierarchy groups, it is similar to the RS configuration we learned in the stereochemistry chapter, based on the atomic number. Okay, so is this E or Z? If you look at the, you basically compare on the same carbon, which one is higher in the order, in the ranking. This is a carbon with 3 hydrogen. This carbon with the 2 carbons. So this is higher. This is higher in the ranking. Just similar as the atomic number ranking in the RS configuration. Okay, so the left-hand side is the hierarchy, higher rank is up. The right hand, this is hydrogen, this is carbon. Of course, this is higher up in the order. So you can see the high order groups have the trans alignment relative to the double bond. So therefore, this is the E isomer. This is E isomer. And if this is one of them being the E isomer, then the other one by quote rotating double bond, that'll give you the Z. This will be Z isomer. So anyway, by losing beta hydrogen, we could have get these two products. But which one we're getting as main product? And that's what the experiment we find out. And very interesting. In the when the actual reaction is done by the base, this base, by the way, is a fairly small base, is hydroxide, small base. And the reason because there's a methyl group, there's a benzyl group, very big, and there's tert-butyl, big chunky T-book just could not access the hydrogen. It has to be a small base. But anyway, what we get is the reaction get, we got only the E product. We got only get the E product. So why? This reaction is E2 reaction. That means the beta elimination, it happens when they both base taking the protons and leaving group leave, a double bond form, all happen at the same time. So what happened? What makes this happen? So the theory, the explanation, and has been proven, by the way, this is hypothesis been proven, it is where suggests the reaction taking place is in the single step, the base taking away protons, double bond form, and the leaving group leave all at the same time, and they have to line up in the we call it anti-coplanarity. Anti means so basically the base supposed to form bond with lone pair. And when the base attack the hydrogen, this carbon-hydrogen bond will break and it becomes double bond. And leaving group leave. All these has to be at the same time. And the lineup between the hydrogen and the leaving group, and it has to be in the anti and coplanar relationship. This is kind of like almost like a trans. Almost like a trans configuration between the boxes, the rectangles that we have. That we call anti-coplanarity. And when the hydrogen just 180 degrees away from the leaving group, that is the moment elimination taking place. And when that taking place, those groups A, B, C, D, we'll assume the position, give you the double bond. So by losing the hydrogen leaving group, I can translate the structure that we saw. Double bond and wedge carbon and dash D, wedge the C and dash D. And this rotate, put it on the paper, and we'll have this kind of product. Okay, make sense, you guys? When the hydrogen and leaving group line up 180 degrees dihedral, that's what we call the anti-coplanarity alignment. So that means depends on, is this being the R or S and this being the RS, you got only very specific one of the alkenes, not either one, not both. You got only one of these two. This is one of the isomers. If this one's E isomer, and the other possibility would be the Z. In our elimination, we find only one of these two, not both. And when that happens, it's simply just because the alignment between the hydrogen and leaving group and two carbons that will form double bond have anti-coplanarity. Another way to, anti-coplanarity sounds very hard. Put it simple, is the hydrogen and the leaving group dihedral is 180 degrees dihedral. Dihedral angle. Dihedral angle is a three-dimensional angle. It's not the two-dimensional angle, but it's related to the two-dimensional angle. So the elimination taking place, there has to be a very particular alignment. And so the explanation for this to happen is the elimination, it is base to attack. And when the base comes, they line up with it to attack the hydrogen. So we're going to break the bond, the double bond will form, and the leaving group will leave. It happens all at once, all together. So there has to be the perfect alignment is required. And so what are the consequences? Basically, if you use a Newman projection, make it easier to see. Newman projection makes that alignment see much better. You can see this is the red one leaving group, this is the beta hydrogen. They are anti, they're in the anti position, staggered and in the anti position. And the rotation of this ball, the rotation of those two carbons, will cause to have the eclipse structure. Okay, we find out this coplanar situation cannot leave, actually is not the moment when the reaction takes place. When you have this alignment, elimination will not take place. Only in this situation, after you take away the base, will take away the hydrogen, and at the same time the bromine will leave, you form the alkene. And this alkene will give you this. And this, as we defined, it is the E isomer, only the E isomers. So the elimination takes some practice, but it requires you to be able to rotate the molecule if necessary, to line up the hydrogen, have 180 degrees dihedral from the leaving group, and then the elimination takes place. And so this is a little practice. Okay, we have it's a simple practice. We have a base, have the elimination, R1, R2. These are dashing. So basically with this, when you can see the hydrogen and bromine both in the just simple line. That means they have the perfect alignment, the anti-coplanarity, or dihedral 180 degrees. When you have that, so I think for you guys to practice, you can keep the way it is. Wedge and dash, just copy first. And you can see the wedge R1 dash R2. Okay, the molecular structure we cannot keep like this. When you put on paper, you should put it two-dimensional. So when you put on two-dimensional, it's R1, R2. You can see both are the wedge. That's important. Okay, I think there's a little very important tip for you to how to decide to. You can see both R1 are the wedge. They are on the same side of double bond. That's the final molecule you write down on paper. Okay. By losing these two, eliminating these two from double bond. Okay, how about the next one? What is this? If you look at this, I feel that these two the same, but you have to look closely. Look closely. This part is the same as my first molecule, and this part is just switched. Okay, that's very important. You gotta really be able to catch those details and by quick compare contrast and find out what's the difference, what's the similarity. So this part is different. And you can use the same trick that I just showed you, but you can now realize these two switched as alkene. We basically get a different isomer than this, by switching these two. So knowing that, then it becomes easy. It takes some practice, but that's why there's Zeppelin homework is for. Take some practice, predict what the elimination for these two products. So one of them, if one of them be the Z, the other will be the E, and vice versa. If one of them is a cis, then the other will be trans. By the way, this particular topic, when we predict elimination with a single beta hydrogen, we will not get the cis and trans because the beta carbon has only one hydrogen, which means you have at least two more carbons. You won't have a cis and trans. You have either E or Z. So predicting elimination product. Okay, so the cyclohexyl halides. This in the elimination chapter is a classic because it combines what we learned about the cyclohexane, the chair conformation, and the axial and equatorial, the preference for these two, and with elimination. So this is the a single chloro cyclohexane. Okay, one chlorocyclohexane. One chlorocyclohexane, the chlorine can be either axial or equatorial. With the equatorial energy being preferred. Okay. By the way, the equatorial, because the chlorine is a heavy atom and it's kind of big. It's bigger than the hydrogen. Bigger than the hydrogen. So therefore, the chlorine is more preferred in the equatorial position, as we learned before. When you have big, more bulky group substituent, they are better, more stable on the equatorial. So when you have the axial, by the way, is not so stable because there are 1,3 repulsion between those hydrogens on the axial position. But for elimination reaction, only the axial position will allow the elimination because if you look at the beta hydrogen, okay, when you have this is chlorine in the axial. Chlorine in the axial, there is a hydrogen on the beta position. It line up perfectly, allow the E2 elimination. Okay, that's when the chlorine is on the axial position. If chlorine on the equatorial, that's a problem. Okay, chlorine equatorial, the anti-coplanarity, this is beta carbon. On this position, this is not a hydrogen. Okay, this is not a hydrogen. And likewise, this is not hydrogen. Therefore, for the chlorine on the equatorial, there's no beta hydrogen available to line up as the anti-coplanar alignment. So that's why the chlorine on the equatorial is not be able to allow the reaction, unfortunately, even though it's more stable. And so that is when the single halogens on the cyclohexane. And regardless beta hydrogen or not, the product will give you the cyclohexene. The product still give you the cyclohexene. There's no doubt. There's only one product. Beta elimination will give you cyclohexene. But when there's the alkyl group, and halogen together, both on the cyclohexane, that becomes very interesting. It's personally my my favorite topic. I really like this to include it in our test. It's more challenging. But that kind of like give you the kick in this topic. So let's see, when there's a alkyl group and it's especially very bulky, like terbutyl, isopropyl, they are together with halide on the cyclohexane. What will happen? So this is the cyclohexane, and you have bromine here, and there's isopropyl here. This is a big, chunky, very bulky isopropyl group. And when this reaction to eliminate the bromine, okay, when you have isopropyl and bromine both on the equatorial, so that means to beta hydrogen, the bromine as a leaving group, it cannot stay on the equatorial to be eliminated. So this molecule, because the cyclohexane molecule can fairly easily twist and turn, and the axial equatorial can be easily switched back and forth, we can have this bromine will has to be on the axial position. So, okay, I put this bromine on the axial position, and the nearby there's the isopropyl. Isopropyl, it has to be the same, the A and E position as the bromine. Okay, you can see both are E, all right? Both are E. But now because the ring can twist and turn, by twist and turn, both groups need to be on the axial position. Okay, remember this we learned in the cyclohexane chapter. Two substituent on the ring, and each one have a certain preferred A or E position. If one of them switch, the other has to also switch, also change. Since both start with E, and to eliminate the bromine has to be on the A position, this isopropyl has to be on A position. Okay, so which beta position has a hydrogen can be eliminated? Okay, this is alpha carbon. Here's one beta. Here's another beta, okay, because the ring structures there's two beta carbon available. The bromine is here, and to eliminate the beta hydrogen has to be the anti-coplanar. In this carbon, okay, this carbon, the beta hydrogen is on the A position. Are you guys following? On this beta carbon, since the isopropyl is on the A position, hydrogen will be on the E position. Okay, so that means. Can you say
that one more time, Professor? I got really confused. Sorry.
Okay, so you have this alpha carbon, beta is let me move my zoom control. It's kind of getting my. All right. This is a leaving group. And the beta hydrogen has to be the anti-coplanar position, the 180-degree dihedral. Both carbon has beta hydrogen. Okay, there's one beta hydrogen here, and this carbon has two beta hydrogens. So these are the beta hydrogens available to be eliminated. It's getting kind of messy. This beta carbon, the isopropyl take the A position. So between, let me kind of put a leaving group in the box, and all the beta hydrogen in the circle. Okay. This hydrogen is not lined up as an anti-coplanar with this bromine. So therefore, this will not be eliminated. Okay. But this beta hydrogen, there are two beta hydrogen on this carbon. This beta hydrogen, it is lined up perfectly with the leaving group. So therefore, this will be removed. By removing this hydrogen, will form double bond here. So the final product, okay, later you can replay the recording. Let me kind of just run to the product. So remember I said this beta hydrogen will not be removed, so that will stay. This bromine is gone. And between these two will form a double bond. This hydrogen is gone, so we have only hydrogen here. And on this beta carbon, there's a hydrogen on the E position. There's isopropyl, stay there. So that is the final product we get. This kind of looks very twisted, ugly. And if you draw the two-dimensional, it looks very nice. Cyclohexane, double bond. This carbon has the isopropyl and it is on the down position. So hydrogen will be the wedge and isopropyl as a dash. You got only this product. Okay, only this product. So later you can rewind, replay the video, and kind of look into what I'm saying here. Okay. Okay, so this is the different substrate. We have the elimination. And if you remember, bromine is a heavier, bigger atom, is really preferred on the E position. Between the methyl group and the bromine is bigger. It's dominant. It's bigger and fatter. He's going to take the E position first and keep the methyl group kind of stood up the methyl group. But anyway, this is the most stable configuration. When we eliminate the beta hydrogen, the leaving group has to be on the axial position. So to do the elimination, we have to redraw the structure, put the leaving group on the axial position. Okay. This bromine is above the plane and on the axial, so the bromine has to be here again. And when this bromine is on the axial position, we need to decide what happened to this methyl group. Is the methyl group still on the equatorial or axial? Well, look at this. Bromine is on the equatorial, and methyl is on the axial. Now the bromine on the axial, the methyl has to be equatorial. That's the nature of a cyclohexane. So the methyl group now becomes here. This is the methyl group. Okay, this is the methyl group. Okay, are we following how the ring twisted and the A and E switch? So far, there's no reaction yet. Okay, there's no reaction yet. Okay, so and then the elimination. And where are the beta hydrogens? We need to find those beta hydrogens. So this is a beta. This is beta. Where are the beta hydrogens? Okay, this one has a hydrogen. And I need to change the color. Getting very confusing. Same color. Okay, so this hydrogen here. This hydrogen belongs to the carbon that is with methyl group. Okay, and the one close to me. This have two hydrogen here. Okay. With this leaving group, and the hydrogen has to be the anti-coplanar or dihedral 180 degrees. We have two hydrogens available. Can you guys see that? One hydrogen is close to me, the other hydrogen away from me. The hydrogen away from me is together with the methyl group. So now I have two beta hydrogen to leave. Which one will be going away? Well, the elimination prefers to form the alkene, and especially when we have a very small base like this. Elimination happens on the to make the alkene has the most substitution. Form the double bond has a more alkyl group attached. So we can form either this is a double bond or this is double bond. By forming this double bond, the alkene has more substituent. Whereas if you form this as a double bond, you get a very plain cyclohexane, and the double bond have only this. So let me draw that. Okay, let's make it easier to see. It takes a lot of time from the lecture. We'll kind of slow down in the lecture. So by forming double bond, we have this as a main product. And the methyl group is here. Methyl group is up, so it's a wedge. This is actually a very particular, very specific RS isomers. So that's why I need to keep the wedge and dash. If I form double bond here, we get a completely different product. Now the double bond has a methyl group, and there's no RS. This carbon is not a chiral carbon anymore. Okay. So we got two possibilities. Which one is likely the product? Well, we just learned the alkene with a more substituent. Even though these two are the isomers, this alkene has more carbon attached. It's lower energy. It's more stable. So therefore, when you have this alkene, this is a cycloalkane, you got this as a major product. By the way, this topic is one of the more advanced topics, and if in the future I put in the quiz test, there'll be the extra credit. I will not test this basic. It takes too much time. I don't have time to explain everything in too much detail. And so this again, when you have a two-dimensional drawing of the cyclohexane, you need to transform to a three-dimensional and then predict the product. But with now I become more experienced. So basically, the beta hydrogen, you can see the leaving group is a wedge. The beta hydrogen has to be a dash to be left. Okay, the beta hydrogen has to be a dash. This is the beta. This is the actual the wedge chlorine. Beta hydrogen has to be the dash. If you look at this one, this is methyl group. The hydrogen will be the wedge. Okay. And you look at this beta hydrogen. This beta hydrogen, you have one is a wedge hydrogen, one is dash hydrogen. Okay, so we have a 1, 2, 3 hydrogens. Which one can be eliminated by the anti-coplanarity? So remember the leaving group and hydrogen in the cyclohexane both has to be the A position, and both has to be the nearby two carbon both in the A position. This hydrogen is already is same as the wedge, so this cannot be eliminated. Only this hydrogen can be eliminated because it is a dash. It's the opposite side of the ring, and when the chlorine adopts the axial position, this hydrogen will be the axial. So because this, and you can see the product, you got only one product, which is this. Only get this as a product, and you will not get the other one. this is not possible. Okay, so take your time. If you go home, take your time, replay this video, and then think about how get to the conclusion. It's a more advanced topic. I know it's kind of a wrap your brains to really figure this out. But once you get into it, you really enjoy it. I really enjoyed this part of organic chemistry. It's three-dimensional. You really have to wrap your mind to really get to figure out. But once you figure out, believe me, this is very, very rewarding. Okay, it's one of the fascinating part about organic chemistry. It's it's visual, by the way. You don't need the mathematical equations, but what you learn about cyclohexane now is coming back. You're going to use that to really understand how you get a product. But I don't have a lot of time for really getting into that. Okay, so I move up, move down. Which for molecules will not be able to go to E2 eliminations. So that's the same idea, just like we covered before. This is leaving group. And you notice this leaving group is a wedge. So the hydrogen has to be the dash. And so you got this hydrogen. This looks good. Okay, this looks good so far. This also looks good because these are the opposite side of the ring. So if the question asks me which one not goes through, I will think this looks very good. You might get a both product, by the way. You get a two product from this reaction. So later I might come back to here if the other one did not work out. Okay, and then we'll look at this. This chlorine is on the wedge, and the hydrogen both on the wedge. Oh no, these two will not be able to have the anti-coplanar relationship with this leaving group. So therefore, this will not be able to go through E2 elimination because the hydrogen and the leaving group has to be on the opposite side of the cyclohexane ring. Okay, so that's